Yeah, good evening, everyone. Welcome to the Domain Analytics program. So we are looking at energy and resources analytics. Today's topic is neural networks. Okay, neural networks, they try to mimic human brains. Okay, neural networks is a study which tries to mimic human brains. It is a part of deep learning. Okay, this is the method which will be studying. So let us see the agenda. Okay, so we'll be learning what are neural networks, what is a neural network primer, perceptron and MLP, MPA, multi-layer perceptron, algorithm, activation function, error surface, also gradient descent algorithm, and one use case. So neural networks, how are they used in energy analytics? Okay, so few examples, neural networks can be used in energy inference mechanisms. Okay, they can also be used to forecast energy use in buildings. Also, they are used for energy analysis of a building. Okay, they can be used to forecast energy. Energy analysis can also be done using neural networks for buildings. Okay, so as we said, neural networks, they try to mimic the human brain. So if you're talking about human brain, okay, the feeling, the sensation, it starts with a dendrites. Okay, a neuron. This is the structure of a neuron we are talking about, a human neuron. Okay, this is where the feeling starts with. The dendrites, various dendrites, they capture all the sensations. Okay, now these sensations, they are fed into this, cell body, and from this cell body, various synapses are sent using this axon. Okay, and from this to different neurons. Okay, so here the first part is, input. This is the part where input happens. This is the part where, processing happens. And this is the transference of signal or signal transduction. These are the terminals of a neuron. So this is a single neuron. Multiple neurons are connected with each other, and they can transfer this signal from here to the brain. Okay, so that it will be processed. Okay, so how does this work? So we are having dendrites, okay, which takes up input signal, the various feelings or various sensations. Okay, these are known as synapses. Okay, they take up these synapses, and after a collection of synapses, we are having this post synaptic analysis, which in the cell body we are having. Yeah, the cell body, it captures, it processes these signals, and it forwards it to the axon as output signals. Okay, so similar to this also, we are having our ANNs, artificial neural networks. Okay, where we are having an input layer followed by hidden layer followed by an output layer. So this this input layers, they act as the input signals. Okay, they take up the signals, input signals. They take up this input signals. Once they are having the signals, they transfer this to hidden layers, where processing happens. It works as the cell body. Okay, signal processing happens. So this hidden layers, they can be of various shapes. They can have a greater number, a smaller number. Okay, so here we are having this, you can say, cell body or cell processing happens in signal processing. Once this is done, signal processing is done. Okay. Then we are having the output layer, which helps to send the output signal. Okay. Similar to working of a human brain, this also works. Okay, now talking about neural networks, they are in machine learning. Neural networks are a machine learning model that are inspired by network of biological neurons found in our brains. Okay, they try to mimic this network of biological neurons. If we talk about types of deep neural networks, there are considerably three types. We are having artificial neural network, also known as multi-layer perceptron (MLP). We are also having convolution neural network, which is majorly used for image processing. Then we are having recurrent neural networks. They are used for many things. They can be used for time series. They can be used for time series and various others. Now, perceptron algorithm, if we are talking about, okay, this is a binary classification algorithm. Okay, they classify into two classes. It is a binary class algorithm, perceptron. Perceptron, we can say it is a unit of our neural networks. It is a single unit of our neural networks. A unit of neural network. This perceptron algorithm. It is a two-class classification algorithm. It is the building block of a neural network. Okay. Building block of neural networks are neurons, weights, and activation functions. Okay. It has a single node or neuron that takes a row of data as input and predicts a class label. Okay. So we can say that this is something like this. Okay. This is a perceptron in which it takes a bunch of data, weighted inputs, okay, and goes through a activation function to give us an output. Okay, it has a single node or neuron that takes a row of data as input and predicts a class label. Now these neurons have weighted inputs. So you can see weighted inputs x1 w1, x2 w2, x3 w3, x4 w4, x5 w5, and threshold values and activation function. Okay, using this activation function, we provide the output taking this weighted inputs. Okay, we'll see the diagram later for this better diagram. Now, this can be achieved by calculating weighted sum of all the inputs and a bias. Generally, it is set to 1. Okay, so it is nothing but w1 x1 plus w2 x2 plus w3 x3 w4 x4 w5 x5 plus our bias. Okay, bias, the extra error term, the weighted sum of the input to the model is called activation. Weighted sum of all the inputs, it is known as activation. Okay, so weight into inputs plus bias. It is the summation of all the weights and inputs plus bias. It is known as activation. If the activation is above 0, okay, the model will output 1. Otherwise, it will output 0. Okay, so according to our activation function, it will predict 1 if activation is greater than 0, or 0 if it is less than or equal to 0. Okay. Now, here as the inputs are multiplied by coefficients, model coefficients, or we can say here the W1 values, okay, weights, like in the case of linear regression or logistic regression, normalization or standardization of data prior using this model will be the most successful approach. Okay, next we are having perceptron algorithm. So we talked about weightage, weighted sum of inputs W1 x1, W2 x2. So how do we decide this weights? How do we decide upon this weight? Okay, so these weights are assigned randomly. First of all, we'll assign a rate, the weight randomly. Randomly initialize the weight vector 0, W0. Okay, and it will be repeated unless we get a repeat until error is less than a threshold gamma. Okay, or max iteration. If you are not getting a minimum value, we'll set a max iteration so that it doesn't enter an infinite loop. Okay. Now for each training example, okay, we'll have to predict the value of yi using current network weights, which are W1, and we will update the weight vector as follows, like this. So new weight will be old weight plus some learning rate into error into x. Okay. So new weight W new will be old weight plus some learning rate into error into xy. Okay, this is the equation we use. Okay, this will be doing iteratively so that we find the correct solution. Okay, so learning rate we have set to 1/3. W0 is 0, 1. Okay, so Wn minus 1 after finding, we got Wn minus 1 is, for x it is coming to be 1/3, for y it is coming to be 5/6. So W1 now is 1/3, 5/6. Okay. So this was the initial weight where z equals to 0. Okay, this line. After initializing, after first correction, we got something like this. Again. Okay, so we did this correction as well, 2/3, 2/3. And we got this line, which is the correct classification line, as you can see. Okay, so previously this was not classifying correctly. This was also not classifying correctly, but this third one, after second correction, we are getting a correct classification. Okay, so if we just see correction of weights, it is nothing but rotation of the separating hyperplane. Okay, this is the hyperplane. It is just rotating. Okay, in this plane. Okay, now let us explain this neuron. So neurons are nothing but this. It is a weighted sum of all the input values. Okay, so x1 w1 into x2 w2 into x3 w3, like this. Here we are having an integration function, which is summation of all the things. So x1 w1 plus x2 w2, like this, up to xm wm. Okay, so here we are adding all the things, summation of all this plus a bias for error. Once this is done, next we'll be moving on to a activation function which will decide whether it will be belonging to which category, this category, this category, this category, this category. Okay. So it is a thresholding logic according to which our category will be chosen. So this is a basic perceptron, you can say. Okay, a basic neuron. It is a single layer perceptron also, you can say. Perceptron. Okay, similarly, that was a single layer perceptron. Similarly, we are also having multi-layer perceptron. Okay, the only difference between a single layer and a multiple layer is presence of hidden layer. Okay, in single layer, there are no hidden layers. In multiple layer, we are having a hidden layer. Okay, in multiple layer perceptron, we can say it is a supplement of a feed forward neural network. It consists of 3 types of layers: input layer, output layer, and hidden layer, where this is the input layer, this first one. These are all hidden layers, and this is the output layer. Now the input layer, it receives signal that is needed to be processed. Okay. The required tasks such as prediction and classification is performed by this last layer, output layer, whether to regress or whether to classify. It is decided in this layer. This layer, it takes just the inputs. Now, hidden layers, the number of hidden layers placed in between input and output, okay, that represents the true computational power of this multi-layer perceptron. Okay, more the number of hidden layers, more will be its computational power, but also it will take more amount of time to compute. Now in this, we are having multiple activation function. According to our need, we'll have to decide which activation function to take. Okay, so this activation function, it decides whether a neuron should be activated or not by calculating weighted sum and further adding bias to it. Okay, now the purpose of activation function is to introduce non-linearity to the output of a neuron. Okay, so if we're talking about activation function, we are having, so this is an identity function, okay, which acts as an activation function. Okay, similarly, sigmoid function, we are having step function, we are having ramp function, we are having. Okay, so if we're talking about step function, here you can see step function will give a value 1 if f is equals to, so it is a function of f. If f is greater than or equal to 0, it will give us a value of 1. Otherwise, it will give us a value 0. Similarly, ramp function, it will give us a value 1 if f is greater than 1, or f if it is in the range of 0 to 1, or 0 if it is less than 0. Okay, it is represented by this graph. Okay, you can see this graph. So basically, it is 0 when it is less than 0. Okay, from 0 to 1, it is giving us the value f, whatever value of f we are having. And here, it will give us a constant value 1. Okay, similarly, here also you can see at 0, it is 0. And here also it is 0. Rest greater than 0, if we are having, the value will be 1. Similarly, sigmoid function, it is given by this formula. Okay, it is like a logistic regression function. Okay, so it will give you a continuous value. Now we can see there are various functions, like we are having this. So these are all activation functions. You can see this functions AF, AF. Okay. So we are having many functions like this: sigmoid, tanh, relu, elu, leaky relu, max out. So sigmoid, if we see, sigmoid function gives us a value like this. It ranges in the range of 0 to 1, but it also gives us a value in between 0 and 1. Okay, so this point to this point, you can see it gives us a value between 0 to 1. Otherwise, ahead of this, it will give us 1 only, and here it will give us 0 only from this point onwards. Okay, between these two, we can have a continuous value. Okay, so this is sigmoid function. Similar to this, we are also having tanh, but tanh it varies from -1 to +1. Okay, similar kind of function you can see, but it varies from +1 to -1. Then we are having relu. Okay, if relu is greater than 0, we are having a value x. If it is less than 0, we are having, or 0 less than or equal to 0, we are having a value 0. Then we are having elu. Okay, so we'll have a value of x if x is greater than or equal to 0, or we'll have a value alpha e to the power x minus 1. Okay, if less than 0. Leaky relu is similar to relu, but here instead of giving us 0 value for less than 0 values, okay, it gives us a value of 0.01x. Then we are also having various others like max out, okay, which gives us the maximum value out of these values. So there are various activation functions. We should be knowing which activation function to use when. Okay, so if we are talking about these all functions, okay, so according to performance, if we you know adjust this, so this logistic, okay, it is having the lowest performance followed by tanh, then relu, then leaky relu, okay, from here to here, leaky relu, then elu. Okay, then we are also having something known as celu. Okay, various you can say activation functions are there. Now also we should remember a few things. Okay, so the choice of initialization, it depends on various other activation functions also. Like if we are talking about relu or leaky relu, if we are having this, okay, we should choose HE initialization. Okay, if we are having celu or elu, okay, this one or celu, we should use Lacan initialization. Okay, there is also something called as soft max or tanh sigmoid. Okay, if we are having all this, we should use Glurot initialization. Okay, so depending on the activation function, we should also choose this. Now, talking about error surface. Okay. Okay. So, if we are talking about error surface, so first of all, we should know the main aim of our neural network is to find the right network for a problem. Means this right network, it includes right architecture, also the right learning algorithm. Okay. Now in this, we are having gradient descent algorithm. Okay. So gradient descent algorithm is a, you can say, iterative first order optimization algorithm that is used to find local minimum or local maximum. So suppose this is a gradient descent algorithm and this is our learning. Or this is a learner having an initial weight. Okay. So it depends on the learning rate as well as initial weight. Okay, this gradient descent algorithm, it is used for various machine learning as well as deep learning methods to minimize cost or loss function. Okay, so basically it will always try to find a minimum value. Okay, this is a minimization technique. Which will try to find always the minimum value. Now suppose this is a very simple one, so it will always find this minimum value. Okay, this is a global minima or global cost minima. But suppose if we are having a graph like this, okay, non-convex graph, we are having, these are known as convex graphs. If you are having something like this, which are non-convex. So suppose our, learner starts here. So it will find this minima instead of this. Whenever it reaches this point, it will say this is a minima point and it will take this minimum. So this is local minimum. Okay, to get rid of this problem, we should, give different initializing, different weights to this. Okay, so that it starts from here. If it starts from here, we'll get a local minimum. Sorry, global minimum. Instead of getting a local minimum, which is this point, we'll get a global minimum, which is our requirement. Okay, now there are various, okay, let me see. There are a few problems with gradient descent algorithm also. If you are setting a learning rate too high, okay, the learning rate, if it is set too high, okay, if learning rate is set too high, learning rate is how speed this moves. Suppose it is too high, so it might never reach here. Maybe it, from here it jumps directly here, from here again here, from here again here. Okay, so it will keep on jumping. Okay, if learning rate is too high, it will keep on jumping and it might never reach a local minima. Okay, so this is known as a exploding gradient problem. Okay, now also if learning rate too low, if you are setting too low that it barely moves. Okay, it moves very slowly or it barely moves. So to get to this minimum point, it will take a very long time. Okay, so this is known as vanishing gradient problem. Okay, exploding gradient, when it doesn't go to a minima value because it is jumping. Vanishing gradient is a problem when it moves too slow, that for it to reach a local minima, it will take a very long time. Okay, these are two problems with gradient descent algorithm. Okay, so for this to correct, you should be aware of setting a perfect learning rate. Okay, this is the main thing you should be aware of, setting a perfect learning rate. Now, let us recollect some of the points. Okay, so neural networks, they are a part of deep learning. Okay, which comes under comprehensive term called artificial intelligence. Okay, so deep learning is a part of artificial intelligence. If we are talking about this, then AI is, the superset, if you say. Okay, followed closely by data science, by data mining, by machine learning, by deep learning. Okay, so of course AI is the superset which encompasses everything. Now, artificial neural network, it is a computational model that consists of several processing elements that receives input and delivers output based on predefined activation function. Okay, here we are using predefined activation function. Then we are having convolutional neural networks. Okay, it is a type of artificial neural network again, used for image recognition and processing. Okay, and it is specifically designed to process pixel data. Then we are having recurrent neural network, which are a type of neural network where output from previous step is fed as input to the current step. Okay, so RNNs are used for sequence classification, sentimental classification, video classification, sequence labeling, part of speech tagging, named entity recognition, and many other things. Okay, it is also used for LSTM in our forecasting, long short-term memory. Okay, many other users are there. Also, artificial neural network, they are consisting of these three layers: input layer, hidden layer, and output layer. Input layer, okay, it accepts input in several different forms. Then we are having hidden layer. It performs all the calculations to find the hidden features and patterns in our data. Okay, hidden layer. Here all the processing, this is the processing part, you can say. This is just input. Okay, if you are comparing this to our neuron, this here, all the processing happens. Then we are having output layer. The input goes through a series of transformation using hidden layer, which finally results in output that is conveyed using this layer. Okay, the association between neuron outputs and neuron inputs can be viewed as a directed edges with weights. So directed edges, we can say, like in network theory, they are directed like this. So it will move in this direction only. Now each input is multiplied by some corresponding weights. Okay, weighted sum of inputs is taken, and it also is including bias, and this gives you something known as activation. On this activation, we'll apply activation function to further classify it or use it as a regression. Okay, now weights normally represent the strength of the interconnection between neurons inside artificial neural network. Okay, and if weighted sum is equal to 0, okay, weighted sum sum of W1 W and X, okay, if it is 0, bias term is added to make the output non-zero. Okay, okay, this is the error term. So basically, if we are talking about equation, it is like y equals to y hat plus error. Error is here bias. If this is 0, y will be bias. Okay, everything will be error. Okay, now let us talk about the use case which I have used here. So it is also a neural network use case for energy efficiency of a building. Okay. So in this study, we are accessing the heating load and cooling load requirements of a building. That is our energy efficiency we are trying to find for a building using the building parameters. Okay. Now this data set, it contains a total of 8 attributes or features. Okay. It is denoted by x1 to x8 and 2 outputs, 2 responses. One is denoted by y1, other is y2. Y1 is heating load, y2 is cooling load. Okay. Our aim here is to use 8 features to predict each of the 2 responses. Okay. So here we'll be making 2 models. Okay. One is for heating, one is for cooling loads. Okay, when we did EDA, we found characteristics of this, something like this. So you can see many are discrete values. A few of them are having some linear kind of relationship. Okay, this is just between our outputs. And when we saw the loss function, the error function, cost function, whatever you want to call it, okay, we found a trend like this. Okay. And when we found, when we saw the actual versus predicted values for y1, or here we can say this heating load. So we found it to be accurate. Okay, in training set and in validation set as well. Okay, this is about the heating load. Similarly, we did this for cooling load as well. Okay. So let us see the coding part of this. Let me go to the coding part. Again, if we talk about this data set, okay, this is a study to assess the heating or cooling load requirements of a building using building parameters as functions. Okay. So the data set information, if we are talking about this, okay, we are performing energy analysis using 12 different building shapes simulated by Ecotech. Okay. The buildings all differ with respect to glazing area distribution, orientation, amongst other parameters. Okay. And we simulate various settings such as function of aforementioned characteristics, all these characteristics, glazing area distribution, orientation, okay, to obtain total of 768 building shapes. Okay. The data set now contains 768 samples and 8 features, and we are aiming to predict 2 real valued responses, okay, which are this heating and cooling load. Okay, this is a multi-class classification problem. Okay. So here about the data set, if we are talking about, this data set contains 8 attributes from x1 to x8 and 2 responses, y1, y2. And our aim is to use all these 8 features to predict the 2 responses. Okay. So these are the 8 response. X1, which is relative compactness, x2 is surface area, x3 is wall area, x4 roof area, x5 overall height, x6 orientation, x7 glazing area, x8 glazing area distribution. Then we are having 2 outputs, heating load and cooling load. Just a second. Okay, so let's start with the coding part. Okay. Okay, so we are loading TensorFlow. TensorFlow is a deep learning library. It is used for neural networks. Also pandas, which is for data manipulation, Seaborn for visualization, Matplotlib also for visualization. Seaborn has a advanced visualization methods. sklearn model selection, we are importing train test split to split our data into train and test data. Also, I'm importing from sklearn pre-processing. Okay, and the data set I have loaded from online URL. You can see. Okay, online URL. We are taking this data. So this is our data. I have loaded this from the online part. So if you want to see this data, I can show you. Let me just go to this URL. Okay, so from here we have taken this ENB 2012 data. Okay. So we are using that data, which is giving us all the values for different buildings. So this is a simulated data we are using. Also, I'm describing the data. So you can see this is the description of data. It is, we are taking the transpose. So generally, if you describe, the count, mean, standard deviation are all here, but we are taking the transpose. So it is all here as column names. We are also showing the pair plot of the whole data set. So you can see. Okay, so very few terms we can see are correlated like x1, x2. Okay, they are showing a negative correlation, and these are not correlated at all. You can see. Okay, y1, y2 are correlated. Let me clear the screen. Yeah. So after doing this, we have created the model. Okay, we have created the model using TensorFlow Keras. Okay, so this TensorFlow Keras, we are importing dense and input, which will be used to make our models. We are also importing model from Keras model. Also from optimizer, we are using Adam optimizer. So input data, we are taking input from this shape 8, which is our total number of columns, all the inputs we are taking. Okay, and we have named it input. Similarly, we are taking a dense layer, which is having 256 nodes. Okay, this is a hidden layer. The second hidden layer. Okay, all are using ReLU. Okay, it is using input data. Dense 1 is using input data as the input. Dense 2 is taking dense 1's output as its input, and output is taking dense 2 as input. Okay. So from this, we are creating the model using this data from input to output. Okay, this whole thing, and we are compiling it using the optimizer Adam, having a learning rate of 0.001. Loss function we are using is MSE, and various metrics which are calculating is MAE, MSE, and name. When we saw the summary, we got this value. Okay, input layer, then dense layer having a parameter this, dense layer 1 having a parameter this, output as this. Okay, so total number of parameters are 68,610. Trainable params are same. Okay, so let's skip this. Yeah. Okay, so we are just differentiating both the, our outputs and inputs and creating also train test data set. Okay. So here we are using min-max scaler to scale our data first of all, and we are also fitting after doing min-max scaler, we are getting the standardized data. We are using this standardized data to do the splitting of the data. Okay, the splitting of the data, train set into test set. Okay, then we are just fitting this model on the train features and train labels. Train features are all the input columns. Train labels are y1, y2. Okay, so you can see the MSE MAPE value, MAE, MSE, and MAPE values we are getting. Okay, because we designed our model to give us these three values. So we are getting this. Okay, and if we are printing the loss function, we are getting a graph such as this. Okay, so loss is very low. So we'll be getting a better accuracy model. Okay, so we just plotting here predicted versus the real values, actual values versus predicted value for training set, validation set. So we are getting quite good values if we can see. Okay, we are getting a straight line. So values are quite good. Similarly, for Y2 also we are doing. Okay, here also we are getting good value. So now let's check the various evaluations. So let us do the evaluation of this input and Y1 and also input and Y2. Okay, so this is nothing but Y1 and its relation with Y1 dash. This is Y2 and Y2 dash. Okay, these relation. Okay, this is Y1 train with training data, predicted train data, Y dash train, Y1 dash train, and Y1 test, also that validation one with Y1 cap test. Similarly, for the second one also we are getting Y1, Y2 train with Y cap, Y1 cap train and Y2 test with Y2 cap test. Okay, and we are getting a very good result. Error also we can see is very minimum, very few errors. So accuracy will be very good. So let's check. Okay, let's check for the accuracy. So for that, we'll be using R2 score, Pearson R. Okay. And MAE, MSE, which we are getting from, which we have already said, R square, Pearson. We are doing MAE, MSE, R square, Pearson. So this is train, this is test. Okay, so we are using this for all the values. Okay. So here also we have done some, formatting, text formatting for this. So let me also tell you about that. Okay. So blue color we have set for all the train data and yellow color we have set for test data. Okay. So let's see. So I'm saying for key in matrix, if train in key, if train is present in this key, okay, print this blue key. Okay, the blue key is this one which we have used. This is nothing but the color coordinates. Okay, so blue key will be this values. Otherwise, it will print yellow key. Okay. So from this, we found out, okay, it has printed y0 and y1, but it should be y1 and y2. Okay, maybe this I had to do +1. Okay, this should be +1 +1. So I'll get y1 and y2. So y1 we see MAE mean absolute error, we are getting very low. Okay, MSE for train MSE for train we are getting also not that much high, but you can see R square value. Okay, 99%, 99.91% of R square value we are getting. Pearson also you can see 99.96. Very good accuracy values we are getting. For test, let us see. Test also very less errors. But check out R square value. Okay, 99%, 99%. For train again for Y2, you can see very less errors. 99% R square, 99% Pearson train. Similarly for Y1 also, you can see very less error and 99% R square, 99% Pearson test. Okay. So as we are discussing, accuracy is very high. Okay, as evident from our, we can say this loss function. So we saw loss was around 0 loss. Okay, meaning no error, meaning accuracy will be very high. Okay, so friends, that was it for our neural networks coding part. And also, this is the last day for our, just a second. Yeah. And this is the last day for our domain analytics program also. Okay, so we have completed our domain analytics program on energy and resources. Okay, so energy and resources, they are we can say are very valuable aspects. Okay, they are required in every field to do work. Okay, and this resources, if they deplete, okay, it will be very hard to continue with our lifestyles. Okay, so we are switching to different forms of energy like renewable sources. Okay, and there will be many more achievements in this field. Okay, this has to be many more researchers are going on. Efficiency is still low in this field, so efficiency is something that we need to increase. Okay, and this ML algorithms, they are doing their part. Okay, machine learning algorithms, they are doing their part to increase the efficiency, but this is a limited efficiency we can increase. Okay, the efficiency, if we change the process, maybe we'll get a better efficiency, but with ML algorithm we will get eventually we'll get an increased efficiency. Okay, means it will limit the losses will be limited. So basically in our energy and resources, using our ML algorithms, okay, we can increase the efficiency. We can increase the, we can say, the scheduling, time scheduling of our power grid. Okay, many other things we can do using our energy and resources analytics. So nowadays we are getting automated apps for these also. Okay, but still, if I see these are on these are in still developing stages. Okay, it is not yet fully developed. So there is a wide you can say space for improvement also. So yeah, friends, this is the end of our energy and resources analytics. So we'll be seeing you again with other programs, other domain analytics programs. So yeah, thank you everyone. Thanks for attending. Yeah, have a good day.